Can we start? Yeah, the door is still open. Can someone close the door, please? Thanks. Thanks, Anja. Okay, so now we have the second morning session with Patrick Huembeli from who is also working with Giuseppe. So again, someone from the EPFL. He did his PhD at the ICFO, and he is also a lifetime member of the PICO through his many visits to Canada. And he's talking about interpretability in quantum machine learning with the Hessian.
Thanks a lot for the introduction, and also thanks for the organizers. It's really amazing to have a in-person conference school again. It feels good to be back after almost 2 years of working alone almost. So yeah, actually, because you just mentioned it, Filippo and we are working with Giuseppe Carleo, the speaker before. So maybe also if you have questions about the things he explained today, we're very happy to talk about it. Are you happy to talk about it? No, just to let you know. So we are kind of knowledgeable about these things. Yeah, so, but my talk will be about a totally different topic. It's going to be about interpretability of quantum in brackets machine learning. We will see if we get to the quantum part. I want to give you just a very short intro to quantum machine learning interpretability. But the main talk will be about interpretability of classical machine learning models with the help of the Hessian, the second order derivative of the laws. Okay, brief outline. So I was really not sure what is your level, where you come from. Are you machine learning experts? Are you just quantum experts? So I will give you a brief introduction to classification, and there's some loop somewhere. Okay. So I will give you a brief introduction to supervised learning, some basics, also notation that I will use. I hope it's not too boring. And if I'm too fast, please interrupt me. I don't have like a clear schedule. We have time, so no problem. Then quick motivation. Why do we need interpretability methods? Maybe just as a warning, I will use what I'm doing, I will call it interpretability, but just to be clear for you, to be primed from the beginning, interpretability is a huge field. I'm just touching a very small part of it, which is this Hessian-based interpretability. So there's a lot to do in this field, especially applied to physics. It's very interesting, but just keep in mind, I'm talking about specific part of this whole field. Then we go into understanding the Hessian of loss landscapes. Like try to understand how does a neural network loss landscape actually look like. This is also a huge playground for scientists. Actually, there's a lot we can still learn. And then I give you some examples where we apply these interpretability methods to phase transition detection. And then in the end, if we still have some time, I will also talk a bit about variational quantum circuits and the Hessian. How does the loss landscape look like there? How can we calculate Hessians in variational quantum circuits? It's not really about the interpretability, but it touches the subject. I have to click, okay. So this work about Hessian-based interpretability of phase transition was together with these people. You might have seen them. So it's no coincidence that I'm here at this conference, I have to admit. But thanks a lot for the invitation. It's very nice to be back with you guys. So yeah, you know, the Michał, Alex, Maciek is also here right now, and the organizer, Anja. Okay, so let's start with some basics. Supervised learning. I assume you all kind of know what this is about. So what is the task of supervised learning? We have some input data, X, and we want and they have some labels or a target output, Y, and we want to find a parameterized function that maps fx to y. There are two main fields of supervised learning. One is regression, one is classification. I will only talk about classification today. You had on, when was that, Saturday, a little discussion about regression. I will not touch this, just that you know that there are two different fields. Classification, why is discrete? So I have pictures of cats and dogs, and I want to sort them by this is a cat, this is a dog, and I want to find some decision boundary, like here shown to the left. Regression, you have normally you have why this is continuous, and you can like summarize regression. Maybe someone will say the contrary, but you can summarize it that we do curve fitting, you know. But this will not be part of this lecture. Okay, examples for classification. As I already mentioned before, we have pictures of cats. We want to put a label on them. We have pictures of dogs. We want to put a label on them. Actually, I'm curious, like MNIST, who of you knows MNIST? Probably most. Now I'm curious, who actually took Python and implemented and actually classified MNIST? Ah, it's almost same set of people. Okay, very good. Then a bit more advanced. Well, it's not that advanced, CFAR or CIFAR. I don't know exactly how to pronounce it. So here we have pictures. Sorry, for those who don't know MNIST. So the task here is you have these handwritten digits in black and white, and you want to classify them by this is a 0, this is a 1, this is a 3, and so on. Then CIFAR is a bit more advanced. You have colored pictures, so you have RGB channels and so on, and you have much more classes like airplanes, birds, cats, and so on. There's many more classification tasks like spam filtering. You want to know, is this email spam? Is it not? Fraud detection. Is this credit card transaction? Is this fraudulent or not? Cancer prognostics, like is this X-ray of a lung? Does it have cancer or not? Finding good job candidates. Is this a valid candidate? And so on. And for us in physics, or what I did with my collaborators, is we look at phase transitions. Does this state come from phase A or phase B? Then models of classification. As already said before, I will actually only talk about neural networks today, but I think it's also very important to keep in mind neural networks is, so often people say machine learning equal neural networks, because it's just probably the most interesting thing to look at, so more challenging. But there are actually very good other classification models like support vector machines, decision trees, naive Bayes, and for example, naive Bayes would be good to do this task here on the lower right, so that you have kind of a sentiment analysis. It's not really a sentiment, but say, okay, I give you a sentence and I want to know, is this sentence about sports or not sports, or is the emotion of the sentence positive, and so on. And these are very simple models. And I also will show later in one slide. Simple models often are easier to interpret, because we kind of see what is the reasoning of a decision tree, because you make always yes, no decision. So it's easier for us to follow this reasoning of a model. Neural networks are black boxes. We really don't know what's going on under their hood. Okay, just in a few words, what is a neural network? I assume most of you know that, so let's make it quick. So the building block of a neural network is a neuron. So here on the top left, a neuron takes an input, for example, the values of the pixels. We multiply it with a weight matrix that is trainable, and we forward it through a nonlinear function, for example, Relu, sigmoid, softmax, and so on. Then a neural network generally is just we take some neurons and put them together. Here, for example, in the lower left, you see a so-called feed-forward architecture, which means that we organize our neurons in layers, and only the outputs of one layer are connected to the inputs of the next layer. the neurons are not connected within the layers for a simple reason that it can make gradient descent and actually train these neural networks. And then the output of a neural network, like shown here, maybe to the right. So we have this handwritten digit, number 6. We take each pixel is a 28 times 28 pixel image. Therefore, we have 784 pixels. We forward this to the neural network, and the output is often a special kind of encoding, which I will talk about. Here's the slide. So we use a so-called one-hot encoding. At least we often do that. One-hot encoding means that for each class we have a separate neuron, and then if a class is so let's take an example here. So the cat would be the first neuron would be firing, and the others 2 are 0. For a dog, the second neuron is firing, and so on. This has a nice perk in the sense of we kind of can interpret the unprocessed output of the neural network if we use a softmax activation function as a probability or as an uncertainty measure. But I will also talk about this later a bit. It's actually not a very good uncertainty measure. There are better ones, which I will introduce with the Hessian. But we can, in the end, kind of interpret the prediction of a neural network, like here in the lower. So basically, this is 0.4%. Okay, that doesn't even normalize to 1. I made a mistake here, but anyway, we have it's like 40%. This is a cat. We have 20%. This is dog. This is 30% a zebra. So we take the class with the highest probability. So this is a cat. Okay. Okay, I mentioned softmax before. Here, this is the softmax function. So just that you know roughly what this is about, but it's not so important for this talk. So basically what we do, we take these, we take the output of the neural network that's unnormalized and normalize it that we can interpret it as probabilities. And then, okay, this introduction was actually longer than I thought. So to train a neural network, what do we do? I give you an image, like here, a number 0, and I propagate it through this feed-forward architecture. And in the beginning, these weights are totally random. We initialize them randomly, so the output will also be kind of random. And then we have to define a loss function, which I will mention in the next slide, to compare how good is the output of this neural network compared to our label, and then we adjust these weights to, in the end, make correct predictions. This is the whole idea behind this. And then if the neural network is properly trained, we input this 9, we propagate it through the layers. Okay, a bit slow, propagate it through the layers, and then we see the neural network says, okay, this is a 9. That it's the whole aim of this kind of supervised tasks. And now I said to train a neural network, we need to measure the quality of the prediction of a neural network, which is basically we need to introduce a measure that compares the predicted label, this y hat here, with the actual label that we are given from the data set y. For example, we can do this with a mean square error here, which compares the inputs, these two vectors y hat and y element wise. Yeah, that's basically it. Okay, and then so to measure the quality of a model, we will look at the empirical risk. So if you have a data set of n, capital N here, so my mouse somehow disappeared. Okay, I have to figure this out later. So we have a data set of n different elements. An element of a data set is an input x and an output y. And to measure the quality of a model, we actually take the sum over all the losses of the whole data set, which is also called the empirical risk. And the aim of this learning then is to actually predict the label of an input that was not contained in this data set, the so-called test point, and to actually improve the prediction of a neural network. Probably also heard about this. We use the so-called gradient descent methods to minimize the empirical risk. And to do the gradient descent, we update our parameters by the gradient of the empirical risk. And often, because data sets in machine learning are enormously big, so it would take a long time to calculate this gradient of the empirical risk, we do a stochastic approximation, which means we take random samples of data to calculate this empirical risk and then take the gradient from it. And probably you've all heard of this is then stochastic gradient descent. Okay, just to summarize for the notation. So we have a data set. I will often use this calligraphic D for data sets. And maybe also kind of important side note, data should always somehow, it comes from some kind of ground truth. For example, here in this case, the ground truth for cats and labels of cats would be the ground truth is the real world. I walk into the real world and I see cats. So I will never be able to capture all possible data sets because there's infinitely many photos I can take of cats. And therefore, the aim of machine learning or these models in the end is not to just minimize some loss, but actually to be good at predicting cats that have never been seen by the model before. It's maybe something important to keep in mind, even though it might sound obvious. Okay, then I have a model parameterized by parameters theta, taking input x, predicting y. I have a loss function that compares this prediction with the actual label of the data set. Then I calculate the empirical risk, which is the sum over all these losses or the average over all these losses. And then I take the test loss of a element that's never been seen by the model. And I actually try to design a model that's good at predicting these test losses. And I do this by minimizing the empirical risk. Okay, one last concept that you might not have heard of and which I will use for one of our methods is the minimal test loss. Because later we will have to take the gradient of test losses. We actually need labels for data that we didn't train on. So basically, in a real world scenario for an unknown input, you will not have a label. So how do you calculate the loss? And there's this idea of minimal test loss, and you just assume that your model prediction is correct. So basically, it's easiest to understand with this example here. If again not normalized. So if your output of the neural network says has this form, so the first label would be the most probable one, then we just assume, okay, this is correct. And then we use y of this form with 1, 0, 0, because we assume the first one is correct to calculate the loss. This is called the so-called minimal test loss. It's just one way of actually calculating losses on data that you don't know what the label is. Yes.
Just a quick question. The minimal test loss does not make sense in a regression setting, or because then it would just be 0, right?
Let me think. Yes. Yes. Yeah. No, it does make sense.
Okay, thank you.
Yeah. No, yeah, it's for classification. You're absolutely right. Okay. Okay, this was a long introduction. I'm sorry. Why interpretability? Errors can actually really matter. There are safety critical applications like, I don't know, error diagnosis, or maybe with cars, you have to classify traffic signs or something like this. And to prevent errors in a model, in a machine learning model, it's actually very important for us to understand where the errors come from. And generally in neural networks, this is very difficult because it's really this such a complicated mathematical model that we in general do not know what is the reasoning behind a certain prediction. So yeah, we can fix errors if you understand where the errors come from. And also for us in phase transition prediction is important to understand how did the neural network come up with saying that this is phase A or phase B. So if we understand the reasoning behind it, maybe we can actually even improve our models to predict phase transitions. Very famous example for machine learning interpretability is it's actually in this paper, it's described here. So what they try to do is they try to distinguish huskies from wolves. It's actually kind of a difficult task. They look similar. And then they realized that so their performance was okay. But they realized that there's quite a lot of false huskies identified as wolves because, and then they used some interpretability method that investigated where does the neural network actually focus on when it does a certain prediction. And they realized it just focused on the background and not on the husky because, and this is something you only realize when you can interpret your prediction, because the neural network model learned that most pictures of wolves were taken in a snowy environment. So the neural network was kind of smart and lazy and just started focusing on the background, and it saw, there is snow, this is a wolf. And therefore all the huskies that are in a snow environment were misclassified, and also the wolves that were not in a snow environment. Other famous example was not so long ago, and it's always again in the news. This paper is about Amazon's hiring tool that had a racial and a sexist bias. This is not necessarily a problem of the model, also of the data, because if you have racist hiring practices in a company, then and you give your past hiring practice to the model to learn, then obviously it will also learn these racist practices. But interpretability again can be used to actually see, okay, so the whatever skin color or the sex of a person is actually relevant for a hiring decision, and therefore we should change the model. And this is not entirely just like an interpretability issue, but also we know that we can confuse neural networks quite a lot by just adding some very small noise. So this is a Gaussian noise here that we add to this image of a panda, and even with a very small amplitude. But this noise is optimized such that the output of the neural network will say this is a gibbon and not a panda anymore. So my talk will not be at all about this kind of interpretability methods, but you can also detect adversarial attacks like this with interpretability. And for those who don't know, like me, what a gibbon is, here to the right, that is a gibbon. Okay, so models versus interpretability. So as I said before, there's quite a lot of different models. And somehow complexity of the model and accuracy is correlated, but also the complexity of a model and interpretability is correlated, but the other way around. So a decision tree, for those of you who know what a decision tree is, it's like a path, you follow a path. Is it rainy today? Is it not? Yes, no. And then if it's rainy, like whatever, you find out if you have to use an umbrella or not, something like this. This is relatively easy for us humans to follow the reasoning of the model because it's built in such a kind of logical, obvious way. Whereas the neural network is on the other side, it's more accurate probably than a decision tree, but it's a black box model, and there's some transition from like support vector machines, random forests, which is a lot of decision trees together, and so on. And then the question is, and so our method with the Hessian is not just focused on neural networks, you can use it on other models. but we will apply it to neural networks. But just to keep in mind, you can also do this with a support vector machine. Actually, for one of the methods that we use called influence function, the original paper was also big focus, this is correct, on support vector machines. And then, yeah, so how can we access the reasoning of a model of a neural network that is a black box? And one way to do that is actually to calculate the Hessian and use Hessian-based interpretability. Okay. To start with this whole field of Hessian-based interpretability, let's first start with the Hessian itself, because a big question in the neural network community is actually, how does a loss landscape of a neural network look like in the parameter space? So here you have a 3D plot. We have two parameters, these are two directions just indicated. But as you probably know, is neural networks often have like millions of parameters. So I don't know how to paint a million-dimensional manifold, but still you would like to know how does actually such a manifold look like to better understand how does actually training work. Because if we do gradient descent, what happens is we just start at some point in such a manifold, randomly initialized, and then we do gradient descent until we converge to some theta tilde here. I will always use theta tilde to indicate that this is kind of the minimum that we found, even though it's not always the global one, it can also be a local minimum. But to understand how actually this mechanism works, and especially because these loss landscapes are highly non-convex, means they have a lot of local minima, how actually is it possible that we don't get stuck in these local minima and still can train these neural networks reasonably well? So therefore, that's the motivation behind this. It's interesting. If you're interested in tasks like this, there's a lot of research that can be done in this direction to understand how does a neural network and loss landscape look like. Okay, so the Hessian, what am I talking about here to the lower left? So one matrix element Hij is calculated by the second derivative of the empirical risk. Again, empirical risk is the sum over all losses of all elements in the data set. If I talk about the Hessian, I will always talk about this kind of Hessian, so pure whole data set. So the second order derivative at your minima theta tilde. And then if we analyze the spectrum of this Hessian, we can actually already start understanding how does such a loss landscape look like, at least around the minimum. And here to the left, you see the blue curve is a randomly initialized neural network, and this is the spectrum. So these are actually points. It's not a line. So these are all the eigenvalues of this Hessian. And if you randomly initialize a Hessian, you will have a spectrum like this, which is like you have to the left negative tail, you have quite a lot, some negative eigenvalues. On the right, you have a positive tail, so you have a lot of positive eigenvalues. But actually, what is most interesting is you have a lot of eigenvalues that are 0. And what that means, I will come to this in a second. And then if you start training your model, or after training your model, your spectrum will change quite a bit, here shown in orange. And because there is still a positive tail, there are still positive eigenvalues, but it's hard to see them. That's why on the right image, you see a zoom in on this positive tail there. And what people found empirically is that the number of positive eigenvalues in the Hessian spectrum is of the order of classes that you want to identify with your model. So if you just want to distinguish cats and dogs, you will only have 2 clearly positive or eigenvalues that are bigger than 0. And here in purple, for example, you see, okay, there's a bit like an arbitrary threshold here, but eigenvalues that are clearly bigger than 0 if is of the order of the classes that you want to classify in your model. For example, here shown in purple, you have 50 classes, therefore roughly 50 eigenvalues that are much bigger than 0 in the Hessian spectrum.
Hello, Patrick.
Sorry, yeah.
Sorry, just a very quick question. So the statement is for the point where your training has converged, basically where the
Yeah, exactly. Yeah, sorry, there left lower theta equal theta tilde. Yeah, exactly. And for the blue one, it's not converged, but just take the random initialization and calculate the Hessian spectrum. Yeah, exactly. Okay, and then one very important thing. I think I come to this on the next slide. Yeah. Okay. Okay. So here you barely see it, but also this orange line has negative eigenvalues. So what does that mean? We always talk about minimas in neural network landscapes. We want to try to find a minima, but often, most times, we don't. It's actually a saddle point because our Hessian has negative eigenvalues. We know it's not positive definite, therefore it cannot be a minima. It is actually a saddle point, but this is not per se a bad thing, because there are theories or conjectures. It's hard to prove these things, but it actually helps us to train these models. Because, for example, Adam is often, people talk when they use Adam with the gradient descent with momentum, they say, okay, you're trapped in a minima, and then Adam kicks you out of this minima. But this is generally not so easy to achieve, even with a momentum method. But if you think of it now that you are not in like a parabolic minima or something with steep walls, but actually in a space that it's mostly flat, because there's a lot of 0 eigenvalues, and even some that are negative, then you see, okay, this momentum method actually help you more escape flat regions instead of like trapped minimas. So it's just like something people often say, maybe, I mean, it's not purposefully, more like people say, okay, we found a minima in the loss landscape, but often it's actually not a minima. It's a saddle point. Okay, and I already start question here.
Hi. So does this mean that in the previous example that you were showing, when there's a little bit of negative eigenvalues, we can still, let's say, optimize this training even more until there are no negative eigenvalues at all?
Yeah, this is a very good question. Not really, because so yeah, I'll mention this later, but it's a bit more subtle. So because if you move along this manifold that you found, which is mostly flat and has some steep directions, the steep directions in the end mean that these are directions in your loss landscape that are well confined by your data. So the data that I give you determines your model, but only in these steep directions, and the rest is kind of free. So negative direction, if you actually move in the negative direction, what you see very fast is that so the loss might go down for certain data points, but it actually will shoot up for others. It's a bit more subtle there, because you don't know how far you're actually allowed to go in this direction, more or less.
Okay, because I had the feeling more or less that since you have so many flat directions, you could always, or like at least try to figure out a path in these flat regions and then adjust a little bit this negative one.
Yeah, yeah. So and one even bigger issue, and I will talk about this in one of the interpretability method, is if you just walk, so okay, we're now in this valley, imagine you're in a valley and it's mostly flat and it's just some directions that are steep. So basically for the empirical risk, this means I can walk in this valley wherever I want and take these parameters and I have the same empirical risk. But it might actually happen that even though I have the same empirical risk, the model is very prone to errors in the test data. And this is something we will look at later, actually. It's a very important issue. So your data doesn't fully determine your model. That's why you have flat regions. And therefore, if you go to another point in this flat region, it might actually, let's say, mess up your test losses. And this is something you want to know a priori, because it might be that you just have a very bad sample of training data. So this is something important in the interpretability context. Okay, thank you. Okay, I think it's, well, I just still say it, but now we already talked kind of about it. What does the spectrum of the Hessian actually mean? No?
Patrick, one more question.
Ah, sorry.
Sorry, I wanted to ask, is this idea the same at the base of the barren plateaus in variational quantum circuits of?
Very good. No, I would say no. So barren plateaus, yeah, so barren plateaus are more subtle. So let's say this way, there's kind of a trivial barren plateau. I would at least claim or call it a trivial one, which is you have a global cost function. And therefore, if you think of a quantum circuit with qubits at least, you can think of each qubit as something like cosinus the 0 state, sinus the 1 state. And then you have a global cost function. So what you will end up is with a cost that's like sinus times cosinus times and so on. No. And if it's global, obviously this string of sinus and cosinus will grow with the number of qubits, with n. And therefore, as long as this sinus and cosinus are smaller than 1, the loss will decrease exponentially, like with the number of n. No? So this is exponentially suppressed. And this is a phenomenon that doesn't really exist, I would say, in the classical realm. No, sorry, I said something wrong. So this is more equivalent to like vanishing gradients with the depth of classical neural networks. Sorry, and now you also have barren plateaus with local loss cost functions, but they come with the depth of the circuit, and this doesn't really have a classical analog. Yeah. Does that make sense?
Okay, yeah. So to summarize, if I understood this correctly, this more relates to the depth. So to make a comparison between vanishing eigenvalues in the context of neural networks and variational quantum algorithm, it's more comparison on the level of the depth. So the number of parameters that you have in the network in terms of depth and the number of qubits, right? And the depth you have in the variational quantum circuits when you increase the number of qubits.
Yeah, and I mean, very importantly, actually, I mean, could have actually been the short answer. As long as you have one eigenvalue that's big, you don't have a problem with vanishing gradients. Yeah. Yeah.
Okay, thank you.
But actually, that took me longer now to come here. I don't know if we will make the quantum part, but it doesn't really matter. We can talk about it later. We also show these barren plateaus in variational quantum circuits with the Hessian. So this is visible. Okay, to this slide, what I didn't want to show. Okay, so how is the Hessian spectrum connected to the curvature of your loss landscape? Maybe that was totally not obvious for some of you. I'm sorry, it's a bit late, this slide. If an eigenvalue is 0, we know that the eigenvector corresponding to this eigenvalue, if we follow it, it's along a flat area in the loss landscape. So what does that mean? Here in this graph, you see it. So we found theta tilde, our minimum, and then I follow an eigenvector that corresponds to an eigenvalue. So here, the lowest one that's just flat, dark blue. We follow an eigenvalue that's 0, sorry, eigenvector corresponding to an eigenvalue of 0. So the loss doesn't change. We're going along a flat direction of our minimum. If we, on the other side, follow an eigenvalue that's very big, so we follow an eigenvector corresponding to an eigenvalue that's very big, we go into a direction of high curvature, and therefore the loss shoots immediately up if you follow this eigenvector. Maybe it's a kind of an important information for you to understand what I mean with these steep directions and so on. Okay, now we come to the interpretability itself, but I already used 45 minutes. Maybe we make now a quick break and then what do you think?
Oh, yeah, then we can do a 15 minutes
It's
break.
just kind of a good
if you
cut
like.
now. Yeah.
Yeah, or if Alex wants to tell a joke. No, okay. Okay, then are there any questions so far right now? Yes, one.
Do you have any idea how the results for the Hessian, so small number of positive eigenvalues, most negative at the end, change for complex value parameters?
Boy. I have to make it short. No idea. I'm not working a lot with complex valued neural networks, honestly. Is there something even like positive definite matrices if they're complex valued?
Yeah, that's the thing.
For complex numbers, I think if you just interpret them as just two real numbers, then everything that Patrick said you can still be applied, and like identically. The only difference is that, I mean, if you want to keep track of holomorphicity of your model, then like basically you're in a more constrained space. So you could get out more information, but let's say everything is said should still be applicable, just that you could get out more and you won't.
I'm not sure if I misunderstood, but you kind of said that when you go along a direction where, I mean, where the eigenvalue is pretty low, you might get into a region where you do badly on the test set. But I don't know, this seems kind of counterintuitive to me, because I'm used to the notion that if you're at a local minima, yeah, sure, you would do badly on the test set. But in flat regions, I don't really see the harm in going along a direction where things don't seem to change much.
Yeah, so I will talk about this later, but basically you're right. Normally you're right, but the chance that you have out of distribution test data is always, I mean, you might always have some data in your test set that is somehow out of distribution, and then this will cause a lot of problems if you do that.
But this seems to be like a data distribution kind of problem, no? Like you kind of like make sure.
Exactly, but so the interpretability method in this case is so we want to be warned by our model that this could happen, and this might actually be useful in certain applications. But yeah, you're generally right. It's not a big issue if you don't have out of distribution points.
Just a short follow-up for this very question. Would you agree, or what could you say about if it might be helpful for a neural network to predict out of distribution data points, like if it would then be helpful to try to not have these eigenvalues of the Hessian that are smaller than 0, like if you could somehow reach this? Like basically, like just like, could this help you in extrapolating better out of distribution? Yes, exactly.
I actually have to think about that. It's a very good question. Yeah.
I would say even in perfect scenario, you go and you have everything is flat. we still show that, I mean, it comes from the flatness. I mean, the problem you don't expect to occur comes from flatness. So like training loss tells you you can around and it's all okay. And then you still find some problem in auto distribution test points. So I'm not sure whether we gain anything out of, you know, getting rid of negative eigenvalues in the end, even if it's possible. Because that's I'm also not sure if it's even possible. So I mean, we in our training we were able to decrease really to small absolute values, the negative eigenvalues, but they were always there. And I from this works you mentioned, I think they always have this negative tail. So I'm not also sure. I mean, I'm not sure if it's well known. For sure, I don't understand what is the fundamental reason for like having this negative tails always.
Yeah.
I will try to say, but it's I'm not
No,
sure what I'm saying. So
it's yeah, I think it's not entirely clear.
I have a related question, I think, because I didn't understand it really. Let me put this in the following way. If the loss function is bounded from below and the set of thetas is compact, or if it's not compact, I can compactify it, then of course there must exist a minimum. So there must exist a point or many points which can be of equal value, which are exactly minima. So they have Hessian values, either positive or zero.
No,
So
I mean,
in a sense,
in theory,
has
yes,
to be
even a
points in which there is no negative tail.
Yeah, but you will never find it in
Well,
practice.
no, never say never. Okay.
No, I mean,
understand. The point is that the method is such that simply it is very difficult to find this minimum. And sometimes you end up with few negative small eigenvalues. But how can you be sure that you are not very, very far from a real minimum in such a case?
From a global minimum.
Well, global, yes.
Okay, now from the global one, we will never know if you're close or not. But so it's a bit more subtle. Now, so one thing I didn't mention so far, because it's probably not so important for this talk, is, but what people also found is that actually local minima, because of overparameterization in neural networks, are not localized anymore, but they become a manifold. So actually they start being connected. So if you go from one local minima that you find, you go along a direction of zero curvature, like along a zero eigenvalue, you will actually always stay in this manifold of local minima. So it's kind of difficult to describe, or I think a lot of people describe it wrongly, in the sense of we're still kind of stuck in this Hopfield network kind of spin glass idea that you have a lot of local, like very expressed local minimas, but this is not true. So it's more a manifold of a huge pool of minimas. Yeah.
Okay, one comment. So it's like there minima that are connected are not all connected to every other minimum. So it's like there are different like sets of minima. Yeah, and the other thing is that there might be a very sharp global minimum, and as far as I know, they don't generalize very well to the test.
I just want to add something more. If you actually have like no 0 points at all, that would mean that for the training set, you basically cannot get a better loss, which I think would be mostly achieved by overfitting. So I don't know if
I think
this is actually something you want.
Said, yeah, that's true. Yeah, if you have a sharp minimum, it's you're too much determined by your training data. Yeah.
Okay, it seems there are no more questions. Then let's have a 15-minute break.
15.
Okay, then let's do a 10 minutes break. And can the last one please close the door? Thank you. Can everyone please sit down? Okay, Patrick, go for your second round.
Okay, thanks. So yeah, Hessian-based interpretability. So now that we know everything about the Hessian, also was very nice discussions. Yeah, okay, so now we know everything about the Hessian. Now let's talk about how we can actually use the Hessian and its spectrum to do interpretability on neural networks. Okay, we start with the so-called influence function. Yeah, by the way, so this is a publication that I have with Maciek, Alex, Michał, Anya. You can find all this basically summarized on archive. If you just look me up or Anya, Alex is probably a bit more, they have a bit more papers, harder to find. Just in case you're curious and you want to have everything written down, it's actually a very well written paper, I would say. Thanks, Anya. And so yeah, these figures are also from there, just as a side note. Okay, let's start with the influence function. So the influence function is an approximation of the so-called leave one out training. And therefore, because it's an approximation of this LOO training, I will just explain the LOO. It's much easier and intuitive than the influence function itself. Leave one out training. So we have a data set, this calligraphic D again. Now I summarize the tuple of data and label X and Y as just, I call it Z, because we will remove it from the data set, like the whole thing, label and input. So what we did so far is we minimized empirical risk of the whole data set and we obtained the parameters theta tilde. Now we remove one single data point from the training set. We retrain the model. We obtain theta tilde without this training point. And then we want to calculate the loss of a test point with respect to both parameters and see what is the difference. Why do we do this? We want to know how influential was this training point ZR that we removed from the training data. And then if we see this delta in loss is smaller than 0, then we know that this training point was a harmful example for the prediction of the test point. If the delta is bigger than 0, then we know this training point was a helpful example. Here again, maybe a bit more illustrative. So to the left, you see we find this red ball is our test point. We put it in our loss landscape. At the, oh, sorry, this should be a tilde here. Oops. So at theta tilde, we obtain a loss landscape, we put our test point. And now we remove one training example and our loss landscape here shown to the right moves. So the point, the test point inside this loss landscape will either move down because it will have lower loss or it will move up because it has higher loss. So if it moves up from the original position, we know it has a higher loss than originally. Therefore, we say it was a helpful example.
Just a very quick technical question. So that loss you compute with respect to the test set or the training set?
Just a single test point.
No, but the loss, the resulting loss you compute with respect to the test data set, or
What resulting loss?
yeah,
iScarf is just an illustration. Yeah.
it's showing.
We,
And
we're,
how do you know that you're not doing like overfitting in this way?
why would we do overfitting? I mean, I just train a model and I'm interested in the test loss of a point or of many points, but I just interested, how does the test loss of a single point change if I start removing training data? And there's no overfitting there because I'm not like retraining specifically for this test point. The question is more, I have a trained model. I have a test point that has some loss. And then I remove training data and I want to see, does the loss of this test point go up or down? The test loss is just there for the test to see what happens to the prediction. Does that make sense, or are you not agreeing?
Yeah, let me maybe wait until a bit further to see actually where you're going. So
Oh,
maybe
okay.
the question was too early.
Okay.
Yeah.
So yeah, but basically here, what I illustrate here, also I have this test point, sorry. I put it in the original landscape. I get test loss, whatever, L. I remove one data point from the training and the loss landscape will move because it's a different training, no? So either the loss goes up, like in the top branch, and then I know this training point that I removed there, like the green dot that I got out of the data set, was actually helpful for this red dot, the test point. I give you an example in a second, maybe it becomes clear. And then in the lower branch, if the loss of my test point goes down because I removed the green point, I know that it was a harmful example. Harmful in the sense of it confused the model and made it make wrong or faulty predictions.
Sorry, one question just to.
I don't see you. Oh, sorry. Yeah.
So when you remove this point, do you retrain with the same initialization or something?
Yeah. Okay, so there are a lot of technicalities to the actual leave one out training. Just as a reminder, we don't do exactly this. We approximate it with the influence function. I'm explaining now leave one out training. Leave one out training is very subtle. So what you do is I find theta tilde, the trained model, and then I also use regularization, and I remove a data point from my training set and I keep on training on the already converged model, even with regularization, because the regularization as shown here in this Taylor approximation makes sure I don't get kicked out to a total of different minima. So it is a bit, there's a bit more subtlety there. But this is a technique that was used to do this kind of predictions. And it's also very subtle changes in the neural network. Does that answer your question?
Yeah. Thanks.
Advocatus diaboli today. Look, I understand. I mean, you are trying to see which are issues important to recognize a cat, let's say, and one picture has some characteristics things which you can interpret. But suppose that you are talking about classification of tissues to recognize cancer. They all look the same, and machine nevertheless is able to distinguish. So fact that you take one figure still for the human will not be able to interpret it. Isn't that so sometimes?
Yeah, that's actually a very good point. I think I even was planning to say something about this. But we can already do it now. This is an issue. And also, sorry, maybe I go directly to these slides. I have some examples. Maybe it also becomes a bit clearer. So these are from the original paper. Somewhere in my slides, there's also the link to this. So it will come later, promise. So this is from the original paper. I have a test image here to the left. This is a 7. Not very obviously, but it is a 7. At least it's labeled as a 7. And I found a harmful training example to the right, which is also 7. But you see, it's a very different style of 7. So it's like the training example here is not prototypical for the test example in this case. So that's why the neural network got confused. And now to come back to your question, Maciek, this is an issue, I agree, because for us as humans, we compare pictures, we look at these results and say, ah, this is a harmful example. Yeah, that makes totally sense because it's obvious that this is a different style of cell. What do you do with cancer images? Well, you actually use this interpretability method to ask the model in its internal representation, which is not accessible to humans, what does it think is similar or harmful or helpful or so. But this is indeed an issue because the results, if you look at images, it makes sense to us as humans, no? But you actually want to quantify this. It makes sense. No, this is the difficult part. And then let me already go to the second example here. So the task here was, I hope I say correctly, to distinguish fishes from dogs. And then we have this test image. This is a clownfish. It's orange. And then we ask, or the authors of this original paper about influence functions, they ask which images are helpful to find this clownfish. And I like this figure because there's also a dog. This dog is a helpful example to find a clownfish. And it's important to keep this in mind because the other species or the other class can be also helpful for another class because probably, and this is again like our reasoning that we try to pressure the neural network to follow human logic, but it would make sense, this interpretation, that this dog is kind of a prototypical dog. It has like a very prominent 4 feet and the tail and so on. So it makes clear to the neural network what is not a fish, and therefore it helps to actually find this fish, the test image there. And then the helpful example from the same class, the fish class, is kind of more obvious because they're all orange. I've never seen an orange dog, so orange obviously helps the neural network to distinguish to classify this fish.
Patrick, can I ask 2 questions?
Yeah, sure. Who's talking?
Just me.
Okay.
Okay, so the first one is, what about leave feature out training instead of leave data point out training? So for me, this is the same thing, but I've never implemented it.
Yeah.
So you know the subtleties, and it might also help with Maciek's question.
Leave feature out. What do you mean?
Just
I
like
cut parts of the image.
Cut the lower half so you don't see the legs anymore or something.
You ask questions. I actually don't know, Anna.
So there are works doing that, but I would say, so this definitely has its merit, but this is great for pictures we understand, right? So we can expect which features to remove, and then we remove them and see how it impacts the model. But I would say with data we really don't understand, and we don't even sometimes we expect some features to be important, right? But it can be it can happen that model found some strange features it finds influential. So, but I would say we're addressing a little bit different questions here.
Mm-hmm.
And with the feature, because this is also important to ask this question, but we ask a different question. So like which images are similar to each other, not like what features are dominant for the prediction in the end.
Okay, thanks. Okay, and my other question is, you said that the prototypical dog was important for the decision.
Helpful.
So can you please help me understand, because in my intuition, it's the more important pictures are the pictures at the decision boundary that change the model behavior, instead of something that you can easily classify.
Okay, this is probably right. We try to show this on simple models, and it's actually not so easy to show with the influence function. Yeah, Anna is already ready to say something. But I'll let you speak first. Then I
No,
give
if
my
you go
opinion.
back to the slides, because that was, I mean,
This one.
no, with these pictures, because I mean, the authors were absolutely, yes, about the dog. So the dog was like a curiosity, so it's still helpful. But the most important helpful points are the ones on the, and I think that's what, because you just didn't say that, but I guess you were coming to that, but then the questions appeared. So the most influential points were the ones in the row, so the fishes or fish, yeah. And then the dog was one of other helpful examples. And actually, I'm also not super sure whether we can say that this is like because there was also an argument in different paper that maybe we cannot really like interpret next influential points as really influential, because I mean, the most influential point is for sure most influential. The
So
second,
the
it's still,
approximation fails in
yes.
higher order,
So-
basically.
So that's why I would be I would be like, I mean, I really like this explanation with the dog, but I'm not sure how certain can we be about this explanation. So
Okay, so then I have to clarify. So the fishes are the most influential points. Yeah, but the dog is a curiosity. That's true. Yeah. There's some more questions.
Yeah.
You're already speaking. Sorry.
So just a curiosity, have people tried to play around with this prototypical image to see what would look like the most prototypical dog and how a neural network could learn a concept in some way?
So she's nodding her head, so she knows more than me. But obviously you can do that. I mean, it's actually a very interesting question. Yeah. So
Have people
Yeah.
done it? Do you know? Or-
Anna, did they?
I think so. I look for the paper, but I don't remember it right now. But
I don't know
yeah,
of
but
it.
I mean, I
it
don't think that
makes
with
total
influence
sense.
functions. I think with some other methods.
Yeah, okay, this I
Yeah,
know,
yeah, yeah.
like that you
Yes,
tune
exactly.
activation, but so it's a bit like dreaming, for example. So you know what dreaming is, no? So you basically try to optimize the input that you get the most certain dog or cat or whatever, and this gives this like super weird, flashy pictures. You could do dreaming with influence, no? So basically you do the same, but instead of like making some activation trigger the most, you make something maximally or minimally influential. This would be doable. It's probably a bit more involved because you have to go through the Hessian all the time. Not sure if it's feasible. It's probably a lot of computation you need. Yeah.
Can I make a small comment? There's this paper, your classifier is secretly an energy-based model. And so it's like the difference here is that the real images, they are lower energy states than artificial images. So if you do something like the dreaming concept that you just explained, you're more likely to end up with real images that you come up with dreaming than artificial images. And so if we conclude this thought, you would be more closer to a prototypical dog or image than if you just do dreaming.
Okay, yeah,
It's a very
makes
nice
sense.
paper. It's
Yeah.
probably hard to compute, but I can recommend it to read it. Oh, sorry.
Yeah, exactly. So, sorry, one sec. So basically, if you dream, no, the images often don't really make sense because they're like, yeah, they're a bit trippy or whatever you want to call them. Ha ha.
One last question, maybe. How do you account for an imbalance in similar pictures? I mean, a picture could be deemed non-influential just because there's loads of it. How do you account for that, or is that?
No, this is actually, yeah, we actually see this. So the influence can go down because because if there's a lot of very similar input data, it determines your, I mean, I come to this in a moment. So it basically determines your model. So if there's a lot of the same data, this strongly determines your model, which means the gradient of, okay, maybe I should go to the explanation, then might become actually clear.
Okay.
Because now we do the approximation of the leave one out training. Ask again if I forget you, but I think it will become clear. Okay. The problem with leave one out training it's really expensive because we have to retrain the model for each data point that we remove. And therefore, we need to have some approximation of this procedure. And there's another question.
Yeah, sorry, it's just a little comment that I think it might fit here because we talked about the feature and learning on the data. And so there is an interesting paper from the machine learning community, which is called Do Deep Generative Neural Network Know What They Don't Know? Or something like that, where they basically show that what you pointed out before, that you can easily fool neural network by adding some white noise. And but another interesting results that they come up with also in the follow-up paper is that instead learning directly on the data, if you learn on a feature space or in a later representation of your data, you can basically make the network more resilient to that. So I think this is also an interesting reading that it's complementary to what we are showing here.
Yeah. Okay. I only have 35 minutes left. No, it's fine. It's really okay. You ask as much as you want. It's really no problem. I don't plan to finish this talk. I have still like 50 slides left, so that's not a thing to happen. So really just interrupt me. Okay, so leave one out training is prohibitively expensive and we don't want to do this. Therefore, we want to have some approximation. And here, I just like put it here. This is the formula of the approximation of the influence function. And I will use the next few slides to explain you a bit what this actually means and also to come back to her question about the frequency of certain training points, how this manifests in this influence function. So to approximate the change in parameters due to the removal of a point, we just calculate the gradient like here. So in this pink frame, even without the Hessian. So to remove a point from our data set, we can approximate how much the influence changes. We can actually approximate this with the gradient. The inverse of the Hessian takes into account if we remove this point from our data set, do we move along a flat direction in our Hessian? Because it's the inverse, it would like amplify this movement, or do we move in a direction of a steep ascent? Because it's the inverse, it would move just a very little. And this comes directly to her question. What does that mean? If we move, or if we have training points that are very frequent, they strongly determine our loss landscape, which means they are the one responsible to make the boundaries or the loss landscape steep. So if we actually have training points that are very frequent, probably the influence will be damped by this because they mostly are in two directions of very steep ascent. Okay, yeah, so the Hessian inverse times this gradient approximates the parameters if some training point is removed. Okay, this is what I already said. So, and if this points into a flat direction, it will move a lot. If it goes into a steep direction, it will be suppressed, and the inverse of the Hessian actually accounts for this. Okay. And then the notion of similarity comes into play. If we talk about similarity of, let's say, pictures, we can compare them in real space. So we just look at the pixel and I don't know, we compare entropy of the images, or I don't know what measures we have here. You can also take the mean square error between these pictures, but this is not necessarily what the neural network thinks is similar. So to compare similarity in terms of what does a neural network see as similar, we need to look at its internal representation. And this we can actually do with the help of the Hessian. And this is more or less what I already said before. So there are two things that determine if the neural network considers 2 points similar. If I have 2 points, doesn't necessarily have to be test or training, just assume 2 points Ci, Zj they are similar according to the neural network if their gradients point into a similar direction, as shown here below. So you have like some test points in black, and the green points that are actually aligned with these test points are similar. But then, sorry, not the similarity, the influence. The similarity is just the direction, and the influence is determined by, do they look into the same direction? And second, does this direction or do these gradients point into a region of flatness or into a region of steep ascent? And this is given by the inverse of the Hessian. And this is what this formula of the influence function actually represents. And then again, what I said before, the training data actually determines your loss landscape, but only in very few directions very strongly. And then there's this region of flatness where our training data actually doesn't determine the loss landscape strongly. And therefore we know the empirical risk will not move or not change if we move inside this enormously big parameter space along flat directions. And therefore, this is also kind of important. Most training points actually will point into direction of steep ascent. But this is, as far as I know, is like empirical result. Yeah, I think make this clear enough. Is this clear? I assume it's clear. Here. Okay, so next interpretability method is the resampling uncertainty estimation. And it's actually, I think, almost one of the most important techniques I show you here, because it's very simple and it's something very important because it's about error bars. How can we know if we can trust our prediction of a neural network? Normally in physics, we're used to put an error bar to every measurement that we do because we need to know how much uncertainty is behind this measurement. In neural networks, we don't really have this. And we would like to actually access some uncertainty measure. And the nice thing, because it's Hessian based, it's totally model agnostic. I mean, there are methods to do error bars in neural networks, for example, Bayesian methods, but they are, well, you rely on Bayesian methods. You cannot just take a support vector machine or a neural network. And now I come back to what I said at the beginning. With we can interpret our neural network output as a probability, but this is not entirely true. So we cannot say, like here in this example, we do two predictions. Yeah, so yeah, it doesn't really matter. So we have two different predictions, y hat 1, y hat 2. Y hat 1 is this 04, 02, 03. So we choose the first class. So if we have to choose a class, we take the one with the highest value. And then we have a prediction y2, which is 09, 005, and so on. So in this naive like framework of saying, okay, this is a probability, therefore I say y2 is a much better prediction than y1. But there's actually no real reason to assume this. It's not like, let's say, a rigorous way of saying, looking at uncertainty of a neural network. And with our resampling uncertainty estimation, we have a more rigorous method to actually do this. Okay, how does RUE work? There are two criteria that are important for the prediction of a neural network. One is called the density criterion, which says basically that the prediction of a test point is reliable if there are a lot of similar training points to this test point in the training data set. And the second criterion, and maybe sounds a bit trivial, the prediction of a neural network is good if you have a lot of these points, and also if the prediction of these training points is actually good. Imagine you have a lot of same examples, but the neural network is not good at predicting them. It's kind of obvious that that then the prediction of this test point will also not be good. Okay, so in other words, a model is good at predicting test points if it has seen similar ones, and it was actually good at predicting these similar ones. And then this is a bit hand wavy. Yeah, maybe I should not put this hand wavy stuff on my slides, but yeah, so the more the better. So if I've seen a lot of examples and I was good at doing it, then it's likely that I'm reliable. And this, the more the better criterion, we're also exploiting a bit later, or it kind of makes sense as soon as I start explaining you the method. How do we actually exploit these two criteria? Okay. Now I give you a new way of notation. It's very simple. So we have an original training data set D here, but with this vector 1, 1, 1, 1, 1. What does that mean? It means it's an encoding for us saying, I use every point of my original training data set once. And then from this original training data set, I start making bootstraps. What does that mean? I take this original data set and I sample randomly from it, but I allow repeated sampling. So I can sample the first one twice, 3 times, and so on. So I get this bootstrap data set, which I encode with this 0, 3, 2. These are random values then, but they mean in this case that the first point, this 0, is never contained. So I just leave away this this example, this training example. 3 means the third one is contained. The second one is contained 3 times. 2 means this third example is contained twice. 1 means the fourth example is just contained once. But does that make sense? Otherwise, raise your hand. It's really just a random sample, and I create data sets of the same size. And then I start retraining my model. So I take these data sets, I make a lot of different bootstraps, and I retrain my model. And I obtain new parameters theta tilde prime, or whatever you want to call them. And then I will make predictions, new predictions on a test point, and see actually how these predictions move. Oops. Little mistake. So okay, because we sample now certain the training points several times and certain training points we don't sample at all, we kind of make use of these density and local fit criteria. And then again, like in the influence function, it's very costly to retrain our models. So we would actually like to do some approximation of this. And this we can actually do in a very simple way with the Hessian, because we just define a bootstrap difference here. This is this W of delta bootstrap. So as an example, we have our original data set is 1, 1, 1, 1. And the bootstrap is 2, 0, 3, and so on. And we just take the difference of these two vectors. I assume this makes sense. And then we can approximate the change in parameters if we retrain our model on a bootstrap just by the inverse of the Hessian, the gradient of all these training data points, and the difference of these this bootstrap difference, which is similar before to the influence function. If we remove a data point, like we go from here from 1 to 0, this is basically what we did before with the influence function. So we just move in the direction of the gradient of this removed data point, and we account for the curvature. Now we do this for many data points at the same time. And if we add a certain data point several times, like 3 times, we just assume or approximate this by a step in the parameter space that's 3 times as big. This is just some sort of approximation. And then we can actually compare training losses. Yeah, maybe just as a sanity check, so assume it's kind of clear now. So our bootstrap difference, this W delta B, has a dimension of M, if M is the number of parameters in the model. No, wait, sorry, N, number of training data in the model. So we have always the same size of training data, and we have the string of I remove or add things to my data set. So I have a string of size N. L is the loss, the gradient of the loss with each training data point as an argument. So this is in the end a matrix of dimension Mn. So n for the training data, and the Hessian is m times n matrix. So therefore, you see that this actually makes sense in certain terms of dimensions. I already showed this before, no? So, okay, yeah.
Just want to make sure that I understand it correctly. So in this update, you have the Hessian, which is from your original neural network.
Yeah.
You have L from your original neural network, and
Yeah.
the only thing you have is your W delta B.
Exactly.
But this is completely just like randomly sample different distributions for your ensembles, right? Like what?
Yeah.
So you don't actually use any ensemble of neural networks here. It's just like somehow features, and I don't see why this would make sense.
Well, it's, I mean, before in the influence function, we did exactly the same. It's just we have the Hessian of the trained model and the gradients of the training points. And in this case, it was the gradient of a test point or just some arbitrary point that we want to compare similarity with, no? And now what, so the idea is really the same. If we remove a point from our training data set, this can be approximated by h to the minus I times gradient of L of whatever point I want to remove. And now the only difference is that I also account for several times putting the same point. Does that make sense? So if I remove it just once, it's exactly the same as in the influence function. But if I add one more, I basically do the reverse direction. So I add a different sign. So I add one more or 2 more, and so that gives me just a prefactor.
Okay.
Does that make sense? No, I mean, you have diagonal elements, no? So no, because it's the second derivative is respect to the. Yeah, so I mean, you also have diagonal terms. You can have the derivative twice in the with respect to the same parameter. Maybe that's. I'm not sure if this is the question, but no, it's m times m squared. Okay, I think I already said most things that I have on this slide. So, and it's also now this question also, it's really the same concept as with the influence function. You remove a point, you get a minus sign. So I maybe see it better before with this this example, no? So originally we had 1 here in the 1, 1, 1, 1, and then we remove 1, so we get a minus sign. If we add 1, we get a plus sign. And if we add more than 1, it's just a plus sign plus some prefactor. So we just assume that the step size, the step inside this parameter space becomes bigger the more we add the same data point. But this is an approximation, but we have to do this approximation. Otherwise, we would have to retrain this model so many times, which is not feasible. Okay. I hope that was clear. Now the last method that we used is the extrapolation score with local ensembles. So there are basically two sources so there's two sources of ways of looking at the extrapolation. So unreliability can come from extrapolation, and there are two sources, ways of looking at the extrapolation, and one of them is maybe the more obvious one, which is making predictions outside of the support of your training data. So just like out of distribution data might be a problem in terms of reliability. But there's also another source, and this is actually your randomness that you always introduce in neural network trainings, which can be random seeds for initialization, but also stochastic gradient descent and so on. So there are several ways how your data underdetermines your model, and they can show up either because of randomness and training, but also if you have test points that are actually out of distribution. Well, I already talked a bit about underdetermination. So what is actually underdetermination? So one way of looking at it is if we start training our model with different seeds, it might actually end up in different local minima or converge to different parameters, theta tilde. And as we've seen before, these theta tilde will have the same empirical risk or very comparable, depends a bit on your training procedure, but let's assume that we will successfully train a model several times with different initial seeds, but we will always end up in a different minima or saddle point, as we've learned before, theta tilde. And now what we actually would like to know from our model is how does this affect our test points? Because we know it doesn't matter for the training data. Our empirical risk will just stay the same, but actually it might be it might lead to very different test predictions, and you would like our model to warn us if this can happen. I have the feeling I already said most of these things, so maybe we can move on and say, just briefly look at how we can actually calculate this extrapolation score. So one way of like, how can we approximate this extrapolation score? Again, we don't want to retrain models several times, is we create this matrix U of M, and this is a matrix that we construct with the eigenvectors of the Hessian, but we remove M, like this, not the capital M. Capital M is the number of parameters. We remove M eigenvectors that correspond to the biggest eigenvalues, because as we learned before, the big eigenvalues are actually the one that are determined by our training data set. So we want to know which directions are actually underdetermined, and then correct for them in with our test loss. And this gives us this extrapolation score. So basically we want to know how reliable is our neural network prediction on a test point in terms of extrapolation, because we want that our test point is actually well determined by our data set, but we cannot really know this, therefore we do this approximation. And this is how we can do this. Then side note here for this technique is, well, how do you choose this small m like this? How many eigenvectors corresponding to big eigenvalues can you remove to have a reliable result? And actually the authors of the original paper of this admit that this is kind of an issue. What we did later to study our phase transitions is we started removing eigenvectors from this matrix UM until we see it converges and it doesn't change anything anymore. And you want this score, this extrapolation score, to be constant. So you start removing them, you recalculate the extrapolation score, and then you see, okay, now we found an amount of eigenvectors that we can remove reliably. Okay. Oh, I'm sorry. Something went wrong here. I don't know what happened. Yeah, the other image you've already seen before. So some practical issues about calculation of the Hessian. We already discussed this a bit in the break. So we always need an inverse of the Hessian. And we know it's not positive definite, so it's not really invertible. So what do we do about this? Actually, there's a really simple trick. So if I give you a Hessian and of a neural network, and you want to make it positive definite, what you can do is you just take the smallest eigenvalue, the absolute value of it, and offset the whole Hessian by these values. Like you add plus the one matrix, the unity matrix, times this parameter. And this is already sufficient. Then you might ask, yeah, why am I allowed to do that? It's a bit nonsensical. I just offset this whole thing. But you can show, and maybe you can actually try to do that later. It's very, like, simple to see. But this is equivalent to L2 regularization. So if I take the second derivative of L2 regularization, shown here, like this lambda of my parameter square, I say take the second derivative of this is just an offset by some value lambda, and we can just, instead of using an arbitrary lambda, we take the smallest eigenvalue, the absolute value, so we make an offset of this negative points, and this is already sufficient and works very well, but is something you need to be aware of. And then the obvious big problem with Hessian is the number of parameters of your neural networks. So modern neural networks have even billions of parameters. And I think every one of you that already trained some fully connected architectures, you see the scales pretty fast to like millions of parameters at least. And this should be avoided, because if you have to calculate the inverse of a million square dimensional matrix, it's just, you will not manage to do that, or you have to do some iterative method, which can also be take a lot of time. So what we did in our case is we tried to reduce the size of our model, size in the sense of the numbers of parameters. One way to do this is, first, don't use fully connected layers, use convolutional layers. And then one important trick that you actually can use is the use of global average pooling. So basically here, so we have convolutional layers, can be 1D convolution, 2D convolution, depends on your architecture. But then what you normally do in a convolution is you have a last pooling layer, like max pooling or whatever, but you have the output is not necessarily very small, because then you flatten all the output of your neural net, of your convolutional layer, to one single dense layer. And then the connection of this last dense layer with your output gives you a lot of parameters if you do it, let's say, sloppy. So there you can actually save a lot of parameters, because this last layer is really just kind of a logistic regression between all the features and the class output. For this, you don't need a million parameters. So what you can do is you take your convolutional layer, the last convolution layer, you use so-called global average pooling, which is for each kernel here, just get one value. So this is a trick that's actually often used. So basically, the number of parameters here in the first, like in your dense layer, will only be the number of kernels in your last convolutional layer. And this is often for like MNIST, maybe 64 or 128, 256. This is not a lot of parameters. So this way, with this global average pooling, you can really reduce the number of parameters, because it has been shown it's not necessary that your last dense layer contains basically the biggest part of your parameters. They should be here in the feature extraction, not in the classification. And that helps you obviously very with your the calculation of the Hessian, because it's much smaller. Okay, now I have a bit of dilemma. We can do 5 minutes variational quantum circuits, or I show you the results of the how we apply actually these classical methods on phase transitions. Yeah, let's do phase transitions. If you're interested in how to calculate the Hessian for a variational quantum circuit, or generally if you're interested in variational circuits, quantum circuits, sorry, we can talk later. And I really just show you some basic results of these interpretability methods on phase transitions. I hope you know what a phase transition is. Most of you, like, kind of.
We talk quite a lot about it, especially this guy.
Okay, good. So yeah, okay, then I can skip this part. Now, so why do we do this with neural networks? Maybe one example. There are problems, like, for example, many-body localization. You don't have to fully understand this. Just main message here is they're really hard to pin down the phase transition, because this is actually not such a, it doesn't seem to be a super hard problem. You have this Hamiltonian, and you know that you have some eigenstates of the form of these spin waves, we call them. So the neighboring spins are somehow similar. And then you add another part of the Hamiltonian, which is a local field with a random sampled HI. So you, for each spin, you apply the field in the z direction, which localizes your eigenstates. So in the worst case of a really strong local field, you should have eigenstates of this form. So they just align with this external field. And we know somewhere in between, these states have to go from this spin waves that are always neighboring sides or very close or look in similar direction to this like random aligned spin. So there must be somewhere a phase transition that it goes from one to the other. And this is like a really hard problem. There are a lot of different order parameters. You need a lot of averaging over eigenstates, and so on is a mess. And we, together with Alex, we try to pin down, for example, this phase transition. But then the problem is, so if you train your neural networks on phases of matter, so you give it, for example, states from deep inside of one of the phases, and you try to find the transition or try to predict the transition with your neural network model, you don't know how reliable this is. It might be that there's just some interpolation between known values, or you really don't learn a lot about actually the physics behind this transition, and therefore interpretability is a big issue. We, with Anna, Maciek, Alex, and Michał, we looked at the different model, not MBL. We wanted to take a simpler model that's well understood, and this is the spinless half-filled one-dimensional Fermi-Hubbard model. It has an interesting phase diagram, let's say. And so if we look at the influence functions, what we see here is, so this is the phase diagram of this Fermi-Hubbard model along one line. And we see here a Luttinger liquid charge density wave transition. It's not so important, and you know what this is about. Just want to show you what we actually see. The question here would be, does the neural network actually learn an order parameter, or does it just like interpolate between some values? And the order parameter in this case is on the left side in the Luttinger liquid. The order parameter is just 0 for all states. So you would expect that the neural network doesn't really distinguish between these states. It looks at them as similar. And then on the right side, you have an order parameter that continuously increases from 0 to 1. So you would expect that states that are close together are the most similar ones. So they're also the most influential ones. And this is exactly what we see here with the influence. So the y-axis in this plot is the influence, and the orange point, the orange line, is the test point that we look at, and we want to know which are the most influential points for this orange line. And we see that if we are in the Luttinger liquid phase, like the first two squares here, is the states inside the Luttinger liquid, they are all kind of equally influential. There's not a big change in the influence because they're all similar. There's a little slope, but this is probably because of finite size effects and so on. But if you go into the charge density wave, the most influential points here shown in green are actually moving with our test point. And this is exactly what we would like the neural networks to learn, because it learns that points close to the test point in the right side of this diagram are actually the most similar ones. So we can say, or be kind of sure that this neural network learns something similar to order parameter and not just like some random feature that we actually are not interested in. And this is actually a very nice result here. So if you look at, so what we do here, I have to stop. Okay, I just finished the sentence. So we have here states, or if we diagonalize these Hamiltonians, we see we have a global sign. So we have psi and minus psi. And this is actually something the neural network should be invariant under. But we see it actually isn't, and we can test this with the influence function. So you see it here on the left side, there's just an imbalanced set. So there's some points with this sign, and they are like outliers. And then we thought, we first didn't understand what these outliers are, but these are actually the training points that have this negative sign. And then we created a balanced data set where we have 50-50 states without and with this minus sign. And then we see in the internal representation of the neural network, these branch actually out. So the neural network starts distinguishing these two states with the sign, even though we as physicists actually would think, so this should be invariant under. And then we know we actually have to improve the model because this invariance should actually be contained in the model. Okay, sorry.
Do you want to say some like summary words?
Yeah, summary is more like if you do supervised training, and I think it would also be in the future interesting to extend this method to also unsupervised problems or semi-supervised problems. Think about interpretability. It's also, I mean, also scientifically for you as a scientist's career is actually a hot topic. There's a lot of things you can do there. And it's also an important problem. And like in every field of AI interpretability is something that people are eager to understand more.
Okay, thanks. We already had a lot of questions, but are there still some questions left? Questions left?
In the previous slide, when you had these plots of the influence and in the, so in the first two plots, could it be that the influence is more relevant because you're actually telling the model, right, these are all pretty similar, but the points at the edge are the ones that determine the range?
Yeah, so the ones at the phase boundary here between this light blue and dark blue region, so they're highly influential, but so we're pretty sure it's because of finite size effects. But this is something we really have to test, and Anya is learning MPS methods so we can go to much bigger systems. So this is maybe future work.
Okay, thank you.
No questions?
Yeah, let's go.
This is one more. It's like, okay. So I really appreciate that So it's like we broke through a barrier that was really engaging, and everyone was like
Mhm.
participating.
Yeah,
So
I
it's
also,
really-
that was
really
a
nice.
very enjoyable talk. Thanks.
Okay, so let's thank Patrick again, and then let's go eat some lunch.
So I have now technical question, because now we should try to take a photo, the school photo. So we'll go outside in front of the building. I mean, the food will be waiting, don't worry. If it's very tempting, you can take side exit to to go directly in front of the building. So we will like make a photo, and then the lunch is there. If it's not raining, hopefully it's not raining. But, okay.